Okay, we should be recording. So welcome everyone to the second of our monthly postdoctoral seminar series. It's really great to see you all. It's my great pleasure to introduce our association's community director, Dr. Kenawy from the Department of Civil and Environmental Engineering. Dr. Kenawy researches the built environment and how to protect it from natural hazards. She's a specialist in advanced nonlinear modeling of concrete structures and in risk characterization for infrastructure as well. She holds a PhD in Civil and Environmental Engineering from UC Davis and a Master's and Bachelor's of Science in Construction Engineering from the American University in Cairo. She's an accomplished scientist, being a recipient of the ASC Aman Research Award in Structural Engineering, the NSF NHERI Summer Institute Grant for Early Career Researchers in Natural Hazard Risk Reduction, and Laboratory Instruction Graduate Fellowship from the American University in Cairo. She has several publications on advancing the simulation techniques of engineering structures, has been an invited speaker at several US institutions and conferences, and has organized technical sessions on structural engineering research and practice as well. She has also held leadership positions in the earthquake engineering community, including as chair of the Earthquake Engineering Research Institute Younger Members Committee. So given these strong accomplishments, it's probably unsurprising that Maha has been offered a position in industry and will be leaving UNR very shortly. So we really do appreciate her making the time to give us this seminar today. And with that, I'll hand it over to you, Dr. Kenawy.
Thanks, Daniel, for the extensive introduction as well. Before I get started, I'm going to be asking the audience to engage with me in a couple of questions. So if you so desire, you can join at vvox.app. This is just put that in your browser and your smartphone, your computer, and then you'll be prompted to enter a session ID. So you'll add this ID. And this way, when I throw these questions at you, you'll be able to participate. Maybe I should also put that in the chat, or Daniel, if you're able to put that in the chat, really appreciate it. So I can go ahead and get started. All right, it's great. So my name is Maha. I work in the structural engineering group in the Department of Civil and Environmental Engineering here at UNR. And today I will be giving a little bit of an intro to some of the themes that I do research on in earthquake engineering, and specifically thinking about what we can do as structural engineers to prepare for large and rare earthquakes. And I think this is pretty interesting because the audience is pretty diverse, so it's going to be quite a nice challenge to talk to people from a lot of different backgrounds. All right, so the first thing I want to talk about is a little bit of introduction about why it's important to prepare for earthquakes in the first place. And I think we can get a pretty good answer if we start to look at maps like the one I'm showing right here. This map is the result of the National Seismic Hazard Project done by United States Geological Survey, where every few years we update these maps that tell us about earthquake hazard, the expected future shaking from earthquakes that we can see over the United States. And so this map tells us about the chance of a damaging earthquake in 100 years over the continental United States. It also tells us about the population density. And one of the outcomes of this project in 2018, the most recent version, is that because of the population growth around the urban areas in the United States, and because of the increased earthquake hazard estimates, as we learn more and more about earthquakes, then more and more people today are at higher risk of significant impacts from future ground shaking. So it is a risk of interest to us. And so that's why we like to study earthquakes and try to prepare for the big ones. So now the logical question is, okay, well, how do we measure our preparedness for earthquakes, right? I think the answer to that is actually not very straightforward. So this has been kind of a moving target. So from the side of structural engineers, in the past, being prepared meant that we design and build structures that don't collapse and kill people. So our preparedness was measured by life safety, making sure that people are safe when there's an earthquake. However, that target has been moving pretty rapidly, actually, in the past couple of decades. So in 2018, Congress reauthorized a program called the National Earthquake Hazard Reduction Program. And this time with focus on what we call resilience-based design, which is a new direction for structural engineers, where not only we think about life safety, but also we want to make sure that we minimize damage to buildings and interruption of community functions after an earthquake. Let me give you a small example of that. If this clicks, yes. So here's an interesting example of a building. This building looks pretty standard, looks pretty average, nothing fancy about it. However, in this building, actually, this is kind of almost a one-of-a-kind building that was finished in San Francisco. It's a resilient multi-unit residence for senior residents of San Francisco. And what's special about this building is that it is actually designed to not only continue to stand, but also remain safely occupied after a major earthquake event. And believe it or not, this is actually not the standard that we build our buildings to. As I said, we just care about the building not collapsing or killing anyone for most of our buildings. But more and more now, structural engineering practice is moving toward making sure that we will not interrupt the functions when there's an earthquake event, and we can prepare for that. So in this building, if there's an earthquake that hits in San Francisco, the residents won't have to displace. They will continue to shelter in place. And of course, that saves us a lot of economic losses, and we don't have to shut down businesses and so on. So now that we talked about our kind of new target now for preparedness, the logical question would be, okay, well, what don't we know? How can we get there? How can we prepare to make sure that when there's an earthquake, we don't have to displace people, we don't shut down businesses, we minimize damage, and we're ready for it? And to talk about that, I'm going to talk briefly about what we do as structural engineers when we do analysis for earthquakes. We start by analyzing the earthquake hazard itself. So we think about what kind of future shaking we will get in a future earthquake. And then we analyze the response of structures to earthquakes. So we figure out if a particular intensity of shaking would happen, how will our infrastructure respond? And finally, we translate the answers that we get from our structural analysis, which usually numbers, into real life damage and analysis of economic losses and downtime and so on. Real life measures that we can talk to stakeholders about. So the problem here, or the problems are that we don't always know how strong shaking in future earthquakes will become. And we also don't exactly know how structures will respond to strong shaking. We know some about that, but as the shaking gets stronger and the structures get more complex, we don't always exactly know. And so these two sources of uncertainty together make it difficult for us to estimate economic losses from earthquakes. And they actually make it more difficult to motivate investment in preparing. For example, to pass policies that allow people to retrofit or mandate retrofit of older buildings or buy into earthquake insurance and so on. So I'll focus on these two areas here, the analysis of the earthquake hazard and the structure. This is where most of my work is. And it may be clear to you why we don't know this information, or maybe not. But really, it's the same old problem that you have in all areas of research. We don't have enough physical observations, and that's why we don't know. And because we don't have enough physical observations, our analytical models are limited. They have idealizations, they're simplified, and we don't always know how to calibrate them properly to predict complex behavior. Okay, so what can we do about it? Well, the answer to this question, I think, will differ depending on who you ask. Structural engineers will give you different answers than policymakers, than scientists. But I think from the perspective of the work I do, the approach we're taking is that we want to work on improving the numerical models that we use to predict earthquake hazard and the response of structures. So we can use these models to supplement the physical observations that are available and then inform our structural analysis and design processes. And hopefully at this point, I've been hinting that this is kind of a big problem that you can't look at from one angle, but you actually have to look at it from several angles. You have to look at the regional scale. You have to see how the earthquake impacts differ over an entire region. And then you have to look at individual buildings and understand the complexities of their behavior and other structures as well. And you have to even zoom in onto what happens at the component scale. So the pieces that you put together to make a building, we need to be able to simulate them properly, specifically the mechanisms that lead the damage in these components. So I'm going to start talking about earthquake hazards. And here's again one of those maps by the United States Geological Survey telling us about the expected shaking in future earthquakes that we have over the United States. This very hot area here is California, of course. The West Coast has a lot of earthquake hazard, as I'm sure you know. Most of my work is on this tiny fault in California, the Hayward Fault. The Hayward Fault is one of the most dangerous faults in the United States because it goes through a very densely populated area, the San Francisco Bay Area. And it is expected to rupture very soon in a large magnitude earthquake and cause significant impacts to this area. But it's not the only interesting seismic area in the West, actually. There's also up in the Pacific Northwest, you have the Cascadia subduction zone. This is at the interface of two tectonic plates, one of them sliding under the other. And so this sliding in this area can cause very large magnitude earthquakes, actually. And so this is also expected to happen sometime soon. And although I don't work on the Cascadia subduction zone per se, but I think it's very interesting. And I'm going to use it to kind of illustrate some of the concepts here. So here's the first question that I would like you to start guessing. So here I am asking you, this is a 2 truth, 1 lie game. Can you guess which of the following statements regarding earthquake hazard in the Western United States is not true? The first sentence is that there's over 10% chance that we get a magnitude 9 earthquake in the Pacific Northwest in the next 50 years. The second one about the likelihood of having a magnitude 7 Hayward Fault earthquake in the next 30 years. And the final statement says that the available earthquake records of these earthquakes inform our preparedness for them. And again, you can type in your browser as it's shown up here and down here, vivox.app, and then you can enter the session ID. And I see a lot of people have already joined, so that's great. I'll wait a couple of seconds. This is a very low stakes situation, so you can just guess. All right, let's call it. Okay, so a lot of different answers here, but I see that 56% of you chose the last sentence as the false statement, and that is indeed correct. So yes, we are expecting these large magnitude earthquakes in the Western United States, and there's very large likelihood that they will happen. Maybe not in our lifetime, but we know they will happen. But indeed, we would use available earthquake records to inform our understanding and preparedness, except that we don't have them. So actually, we don't have any earthquake records for a large subduction zone earthquake in the Pacific Northwest. The last one that happened was about, I think, 300 years ago. And we have very few recordings for a Hayward Fault. We don't have the last large magnitude earthquake on the Hayward Fault, I think, was about 150 years ago. So it was before we invented these recording tools. So what do we do when we don't have recordings? Well, we turn to simulating them. So this is what I do in my work. I work with physics-based earthquake simulations that seismologists conduct to predict future shaking and then help us understand how to prepare for it. And these simulations look like what you're looking at here, except this is kind of just a small representation of the geophysics simulation. They happen over very large computational domains, and they simulate the earthquake rupture and the propagation of the earthquake waves in very complex 3D Earth models. And of course, these are the huge computational effort that is needed for these simulations requires using high performance computing tools. So we use these large, highly parallel simulations on big computers to conduct these simulations. As a structural engineer, I take these simulations on the surface. So you can think of this as you're looking at a map or a plan view of a geographical region. And then at every point in this geographical region, you can get a record of the earthquake shaking. And then using that shaking, you can apply it to our structures. And from that, you understand how you can predict how our structures will respond to earthquake shaking that we can see in a future earthquake. So let's focus on this geographical region here and blow it up a little bit and talk about it. So you can think of earthquakes happening when tectonic plates move relative to one another. There's a sudden slip that happens at a region we call the epicenter, and strike slip earthquakes, two sides of an area across a fault move relative to one another. And the fault is kind of a crack in the Earth's surface, and that leads to release of energy that propagates as waves over a particular region. And these waves cause a lot of shaking to our structures, and this is what causes damage to our structures. So if we think of 3 different locations on the fault in this particular geographic region, and then we simulate a particular earthquake scenario, and then we track the shaking at every station, we will see very interesting observations that these simulations tell us. So we will see how the seismic waves accumulate, and then they can cause these very large pulses. These are velocity pulses that we're looking at. So the ground moves and causes these pulses. And they differ significantly even for locations that are all on the fault. And if we try to see how they affect structures, you probably guessed it. There's a very significant difference in how they affect our structures. So the structures at stations B and C see much more damage than the structure at station A, even though they're all on the fault. And you can think of these red circles as a visual measure of how much damage we expect to see in the structure. So now if we do this over an entire geographical region of interest, put buildings all over the region and track the shaking and the damage that happens to buildings, then we can get pretty interesting stuff. So here's our region of interest. This is the San Francisco Bay Area, and we're looking at ruptures of the Hayward Fault. If we do the analysis that I suggested for the structures, we can get these fancy looking maps that tell us about the spatial distribution of risk to structures over the entire region. Okay, and so what does this map tell us? Well, when I showed this to my husband, he said, "Oh, you really don't want to live here." So, and he had a point, but also we made the point that you don't really get to choose where you live, right? This is the Bay Area. People live all across here. There are so many structures over the fault. There's a huge network of transit, the BART around here. I think there's a stadium in UC Berkeley where the fault goes through it. So you can't really choose not to live around faults, right? But you can, then this is why it's important to look at these maps, because then you can know what are the areas that are higher risk of damage, and then you can prepare for this type of damage that you expect. And you need to also remember that we're looking at complex Earth surface. So different type of soil, different type of topography, and all of that actually impacts earthquake shaking. And we can now measure that using these simulations. So what I mean by that is that we have seen that when earthquake waves travel through soft soils or sedimentary basins, they get amplified much more than they are in stiffer soils or rock. And this amplification translates into higher shaking intensity and also increased shaking duration. And of course, that translates to more structural damage to the structures that are built on soft soils. So looking back at the Bay Area, this is important because west of the Hayward Fault here, this area has softer soils. And so we can expect that there's going to be amplification earthquake shaking and perhaps amplification of the impacts or the damage that we see in structures. So it's important to understand that. Do we account for that as structural engineers? Well, not really well. But we're starting to think about that, and we're starting to think about this amplification and how to incorporate it into our structural design standards. So the ASCE 7 2022, coming out in 2022, will begin to include the amplification effects of the basin of San Francisco and also the basins of LA, the Puget Sound, up in the Pacific Northwest, and Salt Lake City. All right. So shifting gears here a little bit. This whole time I tricked you, I made you think that we can predict damage to structures pretty reliably. And I just convinced you that these maps are, you can just take them for granted, hopefully. But that's actually not true, right? Like I have these numbers that come out of a numerical simulations, and these numbers tell me that the relative displacements between two floors in this building is 7%. And that makes this building high risk. But what does that mean in real life? Does this mean aesthetic damage to the building? Does this mean severe damage? Does this mean that the building will collapse, will have collapse at that point? And perhaps more importantly, how do we translate that into downtime and economic losses that we can talk to insurance companies and building owners about? So these are very difficult questions, and the answers to them are not trivial. And to try to answer these questions, we have to really go back and think about what we are doing in our numerical simulation of the structure, how we're modeling our buildings and other types of structures, and how we're specifically predicting the propagation of damage in our structural components. And this is going to become an important factor in these types of simulations. So this takes me to kind of the second part of what I do in my research, thinking about the complexities of the behavior of structures and thinking about reliably predicting the damage mechanisms and structural components. And I think this is really important to account for and allocate the computational effort toward in these types of simulations to understand the impacts of earthquakes on structures. If you're still not convinced, maybe this will even convince you more. This is a simulation. This is the video, not a simulation. This is a video from an earthquake in Christchurch, New Zealand. So this is very recent. We're looking at this structure over here, and earthquake starts, and then the building collapses pretty suddenly. So hopefully at that point, well, so first of all, I think one of my colleagues used to say that in New Zealand, all the buildings are now earthquake proof. And the reason is all their vulnerable buildings have already collapsed because they have so many earthquakes. And the earthquakes filter the buildings. But the reason why I wanted to show this video is because this is from a very recent earthquake in 2011. The New Zealand building codes are very similar to the United States. So they have modern codes that are designed to resist earthquakes. And yet, because of uncertainties in the earthquake shaking, and because of uncertainties in understanding how buildings will behave, especially older buildings, then we may have these types of extreme damage or collapse that we need to prepare for. So I think there's a lot of work in this area now in understanding these types of damage mechanisms and at the same time developing advanced numerical models that will predict these damage mechanisms and allow us to either retrofit older buildings or have more stringent requirements for buildings in the future that we build them. And a really important step, I think, is also disseminating to practice. So we don't really want these models to just remain as research tools, but we want to make sure that they are being used in practice to predict and assess the performance of buildings in performance-based design applications. And so I'm not going to talk about this too much, but I spent a lot of time in my PhD working on this particular area, predicting the damage of reinforced concrete structures. And I think suffice it to say that we can invest a little bit more computational effort and develop models that better simulate the damage that we see in the laboratory of structural components. And of course, the use of high performance computing tools will allow us to use these expensive simulations and hopefully make them more and more feasible. Okay, so what are the next steps? I think there's a lot of work to be done at the interface of hazard analysis and structural analysis. I think physics-based earthquake simulations will offer a great opportunity for us to utilize high-performance computing tools and radically change the way we do engineering risk assessments and structural design in preparing for earthquakes. There's also a lot of room for creating new models that predict the performance and specifically the damage of both modern and aging infrastructure. And also, perhaps more importantly, creating frameworks that connect these numerical models and the results into real-life losses. So assessing expected economic losses and time needed for the recovery of both structures and the entire community after earthquakes and also other disasters. So on that note, I'll ask you to help me guess again the answer to this question. This is a question about the losses that we expect from a large earthquake. So again, two truths, one lie. One of these is a statement that is not true. The first is about the impacts of a large Cascadia subduction zone earthquake. The statement says that many bridges along the I-5 highway will be heavily damaged in a magnitude 9 earthquake, and the economic losses to Washington, Oregon, and California are estimated to be 70 billion. The second one says that the damage from magnitude 7 Hayward fault earthquake is estimated to be close to $82 billion. And the final one says that many modern buildings in Washington and California will likely collapse in a large Cascadia subduction zone or Hayward fault event. So I'll give you a couple of seconds here to guess. Okay, I'm gonna close the poll now. Okay, this is interesting. So most of you think that the second statement is the false statement. That is actually not correct. So a study in 2016 that actually simulated the impacts of shaking of magnitude 7 Hayward fault earthquake estimated the losses to be close to 82 billion. So that is actually a correct statement. And so is the first one. So if we get a magnitude 9 earthquake in the Pacific Northwest, then indeed we expect to have really expensive damages ahead of us and losses close to 70 billion. Now, the last sentence is actually the false statement. Modern buildings in Washington, California will likely not collapse. because as I mentioned, we design and build buildings to protect lives, so for life safety. So what we hope that our buildings would do is that they would not collapse in a large earthquake. And if there is some percentage of collapse, it will be very low. So definitely not many buildings. So at least we're fortunate to have some confidence in that as structural engineers. And so maybe you're wondering, so why are economic losses from earthquakes are so large? And I think this comes from a lot of different things. So first, you have a lot of damage to aging infrastructure, and we have a lot of that around the country. There is damage to utilities and lifelines. So you have water and power and internet outages that can cost a lot of money. In addition to shaking damage, earthquakes can also trigger tsunamis. They can trigger fires. They can trigger landslides and liquefaction. All of these are really expensive. So there's a lot of economic losses associated with that. So there is, really the key is that there is a lot of time and money that is needed for repairs after an earthquake. Even for modern buildings that we expect to not collapse, they still will probably sustain a large level of damage or even moderate levels that will require repairs to achieve reoccupancy and recovery of businesses and other community functions and bringing displaced people back to their homes. And so the new direction that I talked about at the beginning of my presentation, resilient-based structural engineering or earthquake engineering, helps us or tells us to use this information to inform our analysis and design. So then structural analysis and design of buildings becomes motivated and supported and targeted at the recovery of communities after an earthquake. And this becomes our target. To give a quick example that I will close with, a study in 2016 estimated that in a magnitude 7 Hayward fault earthquake, we may get 0.4% collapses, 5% of the buildings will be unsafe to occupy, and 20% will have to be shut down. But if we invest more money into resilient buildings with more stringent code requirements or retrofitting of older buildings, then close to 95% of the Bay Area population can just remain in their homes and workplaces and not be affected after the earthquake. And so this is kind of the guiding principle for thinking about resilience-based analysis and design. With that, I will acknowledge the projects that I've been a part of. Most of the work I talked about, I did here under Dr. David McCallan. And the project is funded by the Department of Energy. I talked a little bit about some of the work I did at UC Davis, funded by NSF under Dr. Sashi Kunath as a PhD student. And I will thank you for your attention and welcome any questions. Thank you.
Fabulous. Thanks so much, Maha. So yes, please, if you have any questions, feel free to unmute yourself and turn on your video camera and please ask them. And I think I'll stop the recording now.